Okay, thank you for your introduction. So today I will talk about the SPS. So maybe you already heard about that, but unfortunately Matt didn't come, so no one gave the general introduction for the spark plasma sintering. So first I will start with a quite general introduction for SPS, and then we go through the thermodynamic analysis and FEM Analysis that what we got in this year. I hope that the knowledge can be useful for people who are interested with the SPS work and how to use that and how to resolve the problems that you have met in the experiment. So as one kind of the pressure-assisted sintering technique, so I would like first to go through the hot press, heap, and centrifuging. And the difference is that here, all the techniques shown in this picture is that mainly concerns the coupling between the thermal conduction or convection and also the mechanical load. So there is no direct current going through the system. So in hot press, mainly you get the temperature by the heating element, and then the thermal convection, and the heap is similar, and then you have the gas inside, and then you have the contribution of thermal conduction. But for the centrifuge, it's only the thermal convection, and in this case that you have no dye around the sample, and then the sample will be deformed during the sintering. But for SPS, then it's rather similar to hot pressing in some way. And we also applied the hydraulic pressure on the top and down, and then you squeeze the powder into a solid piece when you heat up. But the heat generated by the current passing through the graphite die, and also possibly some current will go through the sample. So in this case, you can get a very high heating rate. So from energy point of view, it's more energy efficient. But generally, for spark plasma sintering, when you read the literature or you did your own experiment, the heating and cooling rate can be in this range from 10 to 600 centigrade per minute. The maximum sintering for the laboratory scale, now it's limited to 2100 centigrade. But the pressure will depend very much on the graphite die. So in this case, that for the normal quality, the normal designed graphite die we can use from 0 to 200 megapascal, because when you increase the temperature, the strength of the graphite will be enhanced. In that case, you can apply 200 megapascal at high temperature, but not at low temperature. So when you sinter the material, we measure the temperature normally by a pyrometer or the thermocouple insert into a hole we drilled on the wall. So there are two kinds of SPS, one from Sumitomo in Japan and one from FCT in Germany. And then in this case, they have different access of the temperature measurement. So FCT have the facility, they measure the temperature from the top. So but using the pyrometer, so they need to drill a hole in the punch and also the ram, and then to focus at a position near to the surface of the sample. But the system produced by Japan is much easier, so you can easily use pyrometer or thermocouple, and also to load the powder will be much easier. So in this case, you can see that compared with the normal hot press and heap, we have one more thing need to be considered is the electrical. So in this case, that I want to give you some examples what you can do with the SPS. So the most literature reported now is concerning the grain growth control. Means that you can get a fully dense materials, but you try to remain as small as possible for the grain size. So in this case, it's very interesting to study the properties of nanostructured material, because they are not so easy to make a fully dense box material. But when we have SPS, it becomes much easier. But basically, you can always find people show you this relative density over the temperature and also grain size. In this case, you can always find that there should be a demarcation temperature that above this limit you will get very quick grain growth, but below that you get very small or slow grain growth rate. Actually, this is quite similar to the conventional sintering, but by the help of the SPS, then we have the external pressure, so we can get promoted densification. Then you can limit the sintering temperature to be low enough to remain the structure. So in this case, we should say that if we only concerning the densification and also to get a small grain size, hot pressing or heap is also similar to the SPS. There is nothing special in this case. But the difference is that for SPS, we normally have a very short time. And then in a very short time, you will get very big change. For example, if we take alumina, this is from a 10 micron alumina powder. If you sinter them at 1150, you get this sub-micron structure. This is only from 300 to 500 nanometer. But once you increase 50 degrees C, and then you get a very comparably bigger size. Both of them will be fully dense, but from the time scale, 50 degree is only 10 seconds, something like that. So by control the grain size, and then we can easily make transparent alumina. So here is I take a picture of the unpolished. This is not polished sample. So once we take out from the furnace, I put on my old mobile phone, and then you see it's really transparent. It's roughly 2 millimeter thick. And this is when we dope chromium, it's a red color. It's quite nice. So nowadays, you can also find this kind of research report in the literature that more people start to use SPS to make transparent. And another application is to make nanostructured materials. So in this case, I use barium titanate to give you as one example. But it's very interesting because we start from similar sized powder. So all of them starting particle size is around 15 nanometer. It was produced by Italian group by Vincenzo. And then, but interestingly that when we got the powder, they detect the chemistry, and then they guaranteed that there is not so much difference. But when we sinter them, it's quite interesting. We based on the same rule that try to get fully dense, but smallest grain size. And then you can find 3 different batches powder, you will get different grain size for the same principle. So this powder, the smallest size we can get is 100. And this is 50, this is 30. And also, for the 30 nanometer materials, we even use a higher temperature. So in this case, it means SPS is quite sensitive processing. Even you cannot detect the stoichiometry difference for the powder, but it will influence the sintering behavior very much. So in this case, SPS could be a good technique that helps you to select powder. But basically, if you want to get a good quality, then you need to guarantee the quality of the powder. As Paul said, that dispersion is really important. And next example is with beta Cylon. So in this case, you can use SPS. This is quite special. In this case, it's totally different from hot press and heap. And then you can control the phase transformation, microstructure, and properties. I didn't know how many people have worked with silicon nitride, but basically, we have the idea that normally people regard the phase transformation and the microstructure. It means the elongated grain growth at the same time. They always think that they are controlled by the same mechanism. But by using SPS, that's the first time we can separate them. So in this case, if we select, for example, for this composition, so we have 2% glass phase inside. And then we hold at 1500. This is the phase composition. So off of the materials will become fully dense after 1 minute. So I didn't show the density curve. So it means that when we get fully dense, beta silon, and then we should get almost 100% already transformed. And if we, this is the density. So you see here it's fully dense. And this is, if we didn't hold at 1500, we just increase the temperature with this heating rate from room temperature. And then we check the phase composition for at each temperature. Then you can find that until 1700 we get fully transformed. And also we get elongated shaft. And then we did a very interesting experiment. This was not included in our nature paper, but this is more interesting. So if you keep the materials at 1500 for 11 minutes, so to the end, you get, this is more like a normal isotropic grain without any elongated grain growth. And the density is fully dense. The phase has been transformed totally, 100% beta phase. But you cannot get any elongated grain. The only way to get the elongated grain is that you need to increase to higher temperature. It doesn't matter if you hold or not at that high temperature, then you will get elongated. But the phase composition will be the same. So in this case, SPS give us more opportunity, means that there must be something different from the hot press. And also in this way, you can easily to modify the microstructure and also the properties. So this could be one benefit. And in the nanocare, we are more interested with to make the near-net shaping, because we have a lot of different components, like hip joints, and Jerome already showed you yesterday that this is new design, so it's very thin. But it will be very critical that how to have a suitable sintering technique to make this kind of component without so much requirement afterwards to polish, because the polishing is not easy. So this is just to give you one example that SPS is possible, and then you can finish the sintering and the shaping in the same time. And this is the size. This hip cup is 55 millimeter in the diameter, and the thickness is 4 millimeter thick. But the success will depend very much on the materials property and the shape design. So the materials properties like thermal expansion coefficient and also fracture toughness will be quite critical to guarantee you can get a complete piece after sintering. Because anyway, we cannot avoid the thermal stress. And now I show you a movie, and then you can see how it works. So this is the computer to control, and this is the sintering chamber. And this is the graphite dye we use, so now we load the powder to make transparent. This is the parameter to measure the temperature. So the working environment is not so clean. So we don't need to make green body, generally. Then we put the graphite dye in. Then you can set up to collect the data of the sintering. This is in how long time you take one data, and then this is a programmer. Okay, we start. And during sintering, only the dye was hot. And you see this is the time. it's 11 minutes. And now we stop at 12 minutes. So after 12 minutes, you get a sample. Including the cooling time, normally if you make a small sample, you only need 20 minutes. So we unload the sample from the die, and then you see you get a transparent small piece. Okay, then that's the general introduction of the SPS. I hope that you get some picture how it looks like and how it works. And then now we start my formal talk. So for SPS, that if we consider the publication in the recent years, this is the statistic up to 2008. So you see this year we get 350 papers on SPS, and this is the tendency. You see in the after 1990 we start to get more, because here it's mainly other kind of similar technique, but it's still not called SPS. And SPS has gone through a history that they developed from AC. So the first generation is normal alternative current. And then they changed to DC. They found that it's more efficient. And then when we found that to change to pulse DC, it will be more efficient. That's the present generation. So normally if you, from all the reports has been published, or the presentation has been given by the people, normally you can find that the advantage of SPS is mainly that you need lower temperature, shorter time, better microstructure control, and also better properties, sometimes, not always. But there are some potential problems with SPS. The first is that the controversial results, because some people maybe used a very high heating rate to get a good result, but sometimes people report you need a very slow speed, or you need high pressure or low pressure. So it's not so it's not so consistent for the results. And also the potential problem comes from the graphite dye. We work with in the reduction atmosphere, and also potentially you will get graphite contamination, especially when it comes to the transparent, then this will be not so good. But the most important thing is that people are still arguing about the mechanism of the enhanced densification, because this will be more interesting to find out, and then to find more potential applications of the SPS. I'm quite fond of these representative opinions. So the first comes from Olevsky from USA. So both of them comes from USA. And he's the first guy to make a really review on the electric field assisted sintering. And he is also good with sintering modeling. And then in his work, that he thinks that it's high heating rate and also initial grain size plays a critical role in SPS. So high heating rate generally can help you to reduce the grain growth and also get enhanced densification, because it has been reported by Johnson in America in 1960s, I think. And but the Japanese people, Komida has done a very interesting work that he tried to sinter the aluminum balls in SPS. It means that it put the already sintered alumina fully dense small balls with the size of 2 millimeters in the die, and then he heat up, try to find what's the potential mechanism for SPS, and then he finds that the local high temperature at the surface will be more critical. And the final, the most new evidence for SPS is that it's very good, because they find that there is no plasma in SPS. So now we can be sure that spark plasma sintering, even we call that plasma, but there should be no plasma. So we need to find other way to explain the enhanced densification. So first, I would like to start from the thermodynamic analysis. So sintering, I guess everyone is quite familiar. So when we have a loose powder, we have a free surface, and then that's the driving force for sintering. We will finally get this structure. But then we have two different access. One is the densification process, one is grain growth. So theoretically, you can have only densification without any grain growth if you go through this way, and then you get no grain growth. But if you go through this way, then you will get grain growth. But anyway, they are realized by different kind of diffusion. So in the sintering theory, you can have surface diffusion, grain boundary diffusion, or lattice diffusion. It depends on the position of the diffused matter. But anyway, they should go to the neck, and then they fill up the space between the particles. Then finally, you consume all the free surface. You get a fully dense. So the purpose of this thermodynamic analysis is try to convince ourselves that are there any effect from the electric current or field, or it's exactly the same as the hot press. So we take a very simple approach. This work has been done by a student from Lyon. And then this is the general densification equation. And then you can describe the densification rate by using different parameters, the grain size or the activation energy. And then what we are interested to see is to see if the activation energy will be changed in SPS. If not, then it means that the controlling mechanism in the densification should be the same as the other kind of sintering technique. So it will be easier. Then we just use the constant heating rate method to measure this data. Then you just transform. If you consider that grain size will not be changed in a limited range of the density, and then you can use this equation to evaluate the activation energy. So the general experiment procedure is that we select 4 different heating rates, 25, 50, 100, and 200, and then we keep the same pressure of 50 megapascal. We also tested with different pressure, but the result will not be showed here. So at each density, you take different sintering curve, you take the same density, and then you measure the densification rate, and then you calculate this number and make a plot, then you get the activation energy. But it's very important because for SPS, it's quite sensitive and also quite quick. So how to get a more reliable data is more important than this kind of theoretical approach. So in this case, you need to correct the baseline, including the external expansion of the sintered material. So in this case, we use the fully dense alumina with the same amount as the powder we will use, and put in the furnace. We numbered the whole setup of the graphite we use every time. Then we measure on the same die in order to confirm the baseline is correct. So in this case, you see this the pink color curve is the original data, and then this is the corrected. So you see now you didn't get the thermal expansion. If the data, the quality of the data is okay, and then normally you will not get this abnormal thermal expansion for the sintering curve. And then, but we have to admit that in the collection of the data, there are some variation because the pulse. And then normally you get some kind of variation for the densification rate, but we can mathematically to smooth the sintering curve because that's a statistic property, so it should be acceptable. And then you measure the densification rate and also corresponding density, and then you make the plot and calculate the activation energy. But first, I would like to say several words about the doping effect. We have tested magnesium oxide and also yttrium oxide and lanthanum oxide, and also the triple doping, U plus Mg, Y, and Le together. So each one is 500 ppm. So in this case, you can find, except for the MgO doping, all the other dopants prohibit the densification compared with the pure alumina. But it's different from the conventional sintering, because in the conventional sintering, even when you dope MgO, you need a little bit higher temperature to sinter, but you will get better microstructure. So in this case, it's not exactly the same. But based on the modeling work, in this case, I think, for example, if we have triple doping, then totally we have 1,500 ppm doping. It means that theoretically it should prohibit the densification more, but experimentally it's similar. So I think for the simulation, we need to consider the real condition to use the result from the simulation, but it doesn't mean the simulation is not correct. And then we summarized the activation energy, and then you see that it's quite good, because in a wide range of the density, it's rather constant. And for MgO, that's the lowest. We only get 300, and the number that are showed here. So the pure alumina, we get 450. That's the average value over the constant range. And then if we can compare with the data got by other people, and this is hot press, creep deformation, and the conventional sintering. So red color is more close to our condition, because they also have the pressure applied. So in this case, you see for pure alumina, it's almost the same. For MgO doped, it has been reduced. But if we compare with the conventional sintering, you can see that conventional sintering gives much higher activation energy. And for the yttrium oxide doped 800, lanthanum also 850. If triple doping, it's roughly 800. So in this case, we have to say that the apparent activation energy of SPS are rather similar to the hot pressing, except for the MgO doped. And also in the density range, normally here we take from 60% to 90%. So in this case, it means because they are quite similar, then we have to accept that the SPS didn't change the controlling mechanism or the controlling species for the densification. The diffusion of the dominating species should be the same. Based on the numbers, it should be still the aluminum diffusion. But the difference when we consider the MgO doped, in this, it's very interesting, because it means that in SPS there must be something extra, not only because we know MgO is quite good to enhance the deformation, superplasticity. So in this case, potentially it means that in SPS, if we want to make doping, if you only want to get help with the densification, and then maybe this kind of doping is quite good. But there are one difference, because anyway, if we compare with the hot press, there are big difference from time scale. SPS normally is 10 times less time for the SPS, for the hot press. So in this case, if we consider the same activation energy, the similar temperature, similar grain size, and then the densification rate has been enhanced for at least 10 times, and then the only potential number can influence this will be this constant number A. So this is normally is a constant which linked with the total number of the active species could be diffused. So in this case, we tentatively to make a suggestion that in SPS, the densification enhancement could be the enhancement of this kind of more active dipoles in the material, like aluminum oxide, because we only test with the oxide. But there are another approach to evaluate SPS. So if we use creep deformation, and then when you take this stress exponent, you can know what kind of controlling process for the densification. So we tried the same, and so that's the simple mathematic change. And then you can evaluate the M value or the activation energy. But the pre-requirement for the estimation of the activation energy is to make sure you get the same pressure stress exponent. Of course, we need to guarantee that no grain growth, so we take a picture on all the samples, we test it up to 1100, and then we found that for pure alumina, when the temperature is 1100, and then already starts the grain growth, so in this case, it's not safe. But by the way we described before, then we can evaluate the M values. You see that mostly that we get number 2. So the values means that in this deformation process of the densification process, that the grain boundary sliding is still the dominating. But once we have a temperature more than some limit, and then we get much higher values of the stress exponent, and means in this case, in this temperature range, you will get dislocation climb mechanism, and then you need to really consider the dislocation formation during the sintering and also how they will influence your properties. So based on this data, we can only calculate the activation energy at 20, because only at 20 megapascal we get stable M values. So pure alumina we get much higher, and MgO doped also has been increased, but it's quite acceptable because we really didn't get a very stable stress exponent, so that will introduce some deviation, but the tendency is the same. Once we have MgO doped, and then we will have much less activation energy, and so the pressure in SPS makes sense that to enhance the superplastic deformation if you have a superplasticity enhancement element inside. So for the thermodynamic analysis, I think that the most important thing that we should to respect the truth that SPS didn't change the dominating densification mechanisms, but it do increase the total numbers of the active species. And at relatively higher temperature, the densification process in SPS is probably accompanied by the dislocation generation and the climbing from the grain boundary, so the dislocation structure and density need to be accounted if you are really serious about the property. But the limit is that it's difficult to get a very stable, and you need to spend quite a lot of time to collect the data. So right now we only collect for alumina. So I think I try to be quick, and yeah. So for the FEM analysis, the main purpose is to see what's the temperature and stress distribution in the dye, in the sample. So then we can know roughly how bad SPS can be, because the most cared issues in SPS is the difference between the temperature in the powder compact and the measured temperature, because we measure the temperature on the surface. So it's people always argue that you have much higher temperature inside. And temperature and stress gradient, which will potentially lead to the problem in the inhomogeneity of the product. It's also a case that in order to get a very good high quality material, especially for transparent, but it's very difficult to measure. So we take the FDM. So we consider the electrical, mechanical, and thermal coupling in this case. So we use the current as the heating source, and then we apply the pressure on the sample, and then we simulate how the temperature and stress will be distributed. But the general initial and boundary conditions are listed here. So we start from room temperature, And then it works in vacuum less than 3 Pascal, so we didn't consider the conduction, thermal conduction in the of gas. But the surface, the heat loss from the free surface are considered. And the temperature, because we have the cooling system, so the two ends of the rams, so the up surface will contact with the cooling circuit. So at that position, we have the room temperature. And we use the current as the control parameter for the input. And we mainly examine the middle plane from A to C. It means that in the middle, the cross-section of in the middle position of the samples. And we used material properties which are function of the temperature and also the porosity in order to make the calculation more precise. And here we use alumina. And the pressure is applied symmetrically. It means that there will be no movement of the sample. And the graphite sheet between the graphite punch and the samples, and also between the punch and the die wall, are approximated by the contact resistance. But the friction between different parts are always considered. And we use the surface temperature. It means the measure temperature as the controlling parameter to follow the whole sintering process. And the software package was called ComSol Multiphysics, because in this case, because we are not, we want to simply use a software package to save time. So in this case, it's very good because they already considered how to make the coupling between different phenomena. And this here we list the properties of graphite and alumina, and you see this here we use alumina 100% dense, so that's only the function of the temperature, but then we linked with the density, this for the room temperature, and then it will be calculated based on this to get room temperature property, and then you will get the real property at high temperature. But the density, we used experimental data. So we use each condition for each size die to record the sintering curve, make the correction, and then we follow to calculate back that what's the density at each temperature. So in this case, we try to mimic the real sintering. And we have examined 4 different dies from 12 millimeter, 20, 36 to 50. That's the upper limit for our machine. So the machine in Lyon should be much bigger, and also for the Spanish in Oviedo. So this is the real size for the setup. So it might be a little bit different if you use different thickness of the wall of the die, or you use different size of the punch. But but now the key point is to compare how it will be influenced. So we want to make the static state analysis and also the transient. Static means that it's equilibrium, it's the final, and transient means that during sintering, it's still heating up. In the process, we just stop the simulation to see how it looks like. So the die size we used 4, and the heating rate we select 3, and the pressure we have 50 and 100. That's the general parameter we used every day. So first we use this FEM Analysis software to use the PID modular to control the temperature. So then we don't need to set up the temperature manually. So this is the programmed temperature. So normally you hold temperature at 600 for 3 minutes to get stabilized, and then you heat up with fixed heating rate, and then this is final dwelling temperature for a period, and then we shut down. So this is the simulated current input in order to get this curve, the real temperature. So it's rather similar to the real experiment. So we think now the control, this modeling should be quite reliable. And first, we take a look on the die size effect. So if we take the moment that we reach 1300, so now we set up 1300 as the final sintering temperature. So if once the temperature at the surface reach 1300, then we make a plot. So this is quite a little bit tricky because you see there should be a displacement because we have the densification process. But in this case, when we want to make this kind of plot, it's not possible to include the geometry change. So you can see for 12, 20, 36, 50, when you increase the die size, and then in the sample, and then it seems that bigger size becomes more homogeneous. It's not as we expected, but only from this color picture, it's not so precise, so we can show more data. But always, when you before you start to equilibrium at the final sintering temperature, you see the highest temperature is always in the punch, not in the sample. And also, when you measure the temperature, you really need to be careful because it's quite sensitive to the position of the surface. In the middle, at the position to the same level as the sample, and then you will get the correct temperature. Otherwise, you will get the temperature overestimated because here the temperature is lower. If you measure temperature here, then inside you will get much higher. But once you hold at the final sintering temperature, and then the gradient in the punch will be reduced very much. And also in the sample, you get more homogeneous temperature distribution. So it means that it should be not a very big case. But we still want to show you some real values. So if we use 12 millimeter die, and then this is the moment that we reach the programmed 1300, it means that depending on the heating rate, so the higher heating rate, the machine will get some difficulty to follow. So in this case, normally, the highest heating rate gives you lowest measured temperature on the surface. So in this case, that the lower heating rate, the real temperature in the sample will be the highest. But we need to respect the truth that here, the surface temperature is different. But we say that's a program, because now I want to show you in a very short period, when we reach the program 1300, and then we go to the real 1300, and how the temperature will be changed. And also, we will show the equilibrium state. So in this case, if you think about the temperature gradient from the outside the surface to the center of the sample, so the difference is for 12 millimeter, it's around 75 centigrade. But in the material, if we only consider the temperature gradient in the material, it's not as much as this, so it's only 20. But when we come to the real temperature of 1300, and then you can see the lower heating rate will give you the lower temperature in the material, and then so it means that a lower heating rate will be good if you really want to control the temperature inside. But basically 100 and 200 make no difference. But once you equilibrium at the final sintering temperature for 2 minutes, and then we didn't get any influence from the heating rate, that's quite general. And then we analyzed, we used a parameter called the temperature gradient, means that the temperature difference at unit in the unit distance. And then you can see that for this small die, it can be very high. It's close. The highest position is 1 millimeter in the sample, and in the die it's 4. I think it's 4 millimeter from the interface. And then when we change the die size to 36, and then the shape of this temperature profile will be changed. So in the small die, then we have a relatively sharp change at the interface position. But for the big die, we have a quite round shoulder. But the tendency is similar when we reach the program temperature. Its lower heating rate will be higher. But once we start to reach the final sintering temperature, because the system will reduce the current automatically, and then we get difference, the higher heating rate will give you higher absolute value in the temperature in the center, and then the difference can be as high as 150 if we use 36 millimeter. But inside of the sample, the temperature difference is not doubled, because here is doubled. But the temperature difference in the sample is rather smaller, and this is only 40. If we equilibrium at low temperature, and then from here, you see it's around 33 centigrade in the sample. And also you can find when you increase the die size, and the temperature gradient in the sample becomes lower compared with the 12 millimeter. So it means that it doesn't mean that bigger size always to be bad. So for the instance of the static state, I think the increase of the die size will increase the temperature difference, but the increase of die size didn't change the temperature difference in the sample so much, only a difference of 8 centigrade when you increase from 12 to 36. So that's a good news. And the increase of the heating rate makes no sense for the temperature difference if you consider the equilibrium, but for the transient transition state, and then the heating rate will change, because once we reach the final sintering temperature and the equilibrium, no change in the temperature. And then we also want to see if the pressure will change the temperature difference, and then unfortunately that we didn't get so much influence, but anyway it seems that higher heating rate, when you change the pressure, it have a little bit influence. And for the stress distribution, it seems quite stable. It doesn't matter how big you use and how fast you have the heating rate. And but then if we put to reduce the temperature, so this is for different size, and then we consider the different dies, and then you see the 20 millimeter is the worst. And then if we increase further to 50, actually the temperature distribution has been improved. So it's also meet our experimental result, because from the beginning I also feel quite strange. When we measure the grain size distribution in 20, it's very bad, but the 36 is a little bit better. But now I think it's quite good, we understand. So if we consider the lower temperature, then you see that's the similar tendency that for the larger size die, the profile will be changed, but you get more stable in the sample. Of course, you get a bigger difference between the real temperature inside and the measured temperature. But the good news is that we always consider the temperature is a relative value. So in this case, it means that if you select correct die size and heating rate, you can improve the homogeneity. So then I neglect the summary. Thanks for your attention, and any questions?